fitting lines to data points, modeling linear functions. We have both exact and approximate linear models that we can find functions for. We've seen that if the data points fit exactly on a line, we can use two of the points to model the linear function, or write the equation of the line. We can determine that the data points fit exactly on a line by determining that the changes in output values are equal for equal changes in input values. In this case, we say that the inputs are uniform and that the first differences are constant. Now, if the first differences of data outputs are constant for uniform inputs, the rate of change is constant, and a linear function can be found that fits the data exactly. If the first differences are nearly constant, a linear function can be found that is an approximate fit for the data. Let's see how first differences are done in example 1. The table gives the annual retirement payment of a 62-year-old retiree with 21 or more years of service at Clarion State University as a function of the number of years of service and the first differences of the outputs. You can see the number of years of service at top and our retirement payment given those number of years of service. When we take the difference, we get $1,950 each time. So we should be able to find a model that computes this exactly. So first we're going to compute the rate of change of the function and then use one of the data points to write the equation of the linear function that models the retirement payment. So to find the rate of change, let's find the difference in the y over the difference in the x's. So we have 42,900 minus 40,950. I'm just choosing the first 2 points, divided by 22 minus 21. So then we get 1,950 over 1, which is 1,950. That's your slope, or your rate of change. So from 1 year to the next, the retirement payment will increase by $1,950. Now, to be able to get the equation of the linear function, we just need to use this slope and one of the points. I'll go ahead and choose this point. So I'm going to have a y minus the y value equals the slope times x minus the x of that point. And then we'll go ahead and solve for y. $21 times 1,950. I get 4,950. And so y is going to be 1,950 times x. So we can even check to see that this works with each of these inputs. If you want to do it quickly, you can put this y equals 1,950x into your grapher, but then set your table so that we start at 21. So when we look at our table, we have year 21, you have a retirement of 40,950. Year 22, 42,900. Year 23, 44,850. 24, 46,800. 25, we have 48,750. So it does fit the data exactly with this one function. Linear regression. We can determine the equation of a line that is the best fit for these points by using a procedure called linear regression. The procedure defines the best fit line as the line for which the sum of the squares of the vertical distances from the data points to the line is a minimum. For this reason, the linear regression procedure is also called the least squares method. In example 2, we have a table that gives the projected population in millions of females in the U.S. under the age of 18, projected for the years 2020 through 2060. We are to draw a scatter plot of the data with the x value of each point representing the number of years after 2000 and the y value representing the population of females under the age of 18 in millions. So let's go ahead in our calculator into the stat editor. We can put this data. Now our year is going to be aligned to the year 2000. So this is going to be an x of 20, 25, 30, 35, 40, 45, 50, 55, and 60. So we can enter that into our calculator here. Just double check to make sure that you didn't type anything incorrectly. And then they've already scaled the outputs to be in millions, so we're going to put that raw data in. Double check to make sure you didn't have any typos while entering that data. And then we'll make our scatter plot. So the first thing that we want to do is go into the y equals. Go ahead and clear out that function from before. Scroll up onto plot 1 and hit enter. Now when you move off of the plot 1, you can see that it's highlighted. So it's going to plot the data that you've put in L1 and L2 by default. Let's do a zoom. Zoom stat is option 9, and it'll make a nice window around your data points so you don't have to manually put those in the window. I'll go ahead and copy this to use as our scatter plot. Okay, graph the equation y equals 0.1x plus 36 and the data points on the same axes. They want to know if this is a good fit for the data. So go back to your calculator and in y1 type 0.1x plus 36 and hit graph. I would say that this is not a good fit for the data. Now use a piece of spaghetti or pencil lead, something that's nice, straight, and skinny, to find a line through two of the data points that's a good visual fit for the points. Use the 2 points to write the equation of this line. Then type the equation into your graphing calculator. So I'm going to use a drawing tool of a line, and I'll adjust it. You can use whatever spaghetti noodles you have, or a piece of pencil lead. You know, I honestly think that from the first point to the last point might be a good fit, or maybe even the second point to the last point. I think that is an even better fit. So your answer may vary depending on what you see as a better fit, but I'm going to be using this point and this point to find my equation. So first I need to find my slope. Slope is 38.2 minus 43.6 over 25 minus 60. Go ahead and put that into your calculator. I have 38.2 minus 43.6, all being divided by 25 minus 60. Okay, double check to make sure you have no typos. And there is our slope. So slope is, we'll say approximately 0.1542857,143. Okay, and then I need to use one of those points that I used for finding the slope and the slope to get the equation of the line. So I'm going to say, let's use the first point, y minus 38.2 equals my slope of 0.154. I'm just going to record that, but I'll use this number that's in my calculator over here. There's even more digits that are not shown on your calculator, so best to use that in your future calculations. And I've got an x minus 25 there. So y minus 38.2 equals 0.154x minus, I've got 25 times that slope number, and I get 3.857. Okay, so I'm going to take and add 38.2 to both sides, which means I'll have y equals 0.154x plus 34.34. All right, looks pretty good. Let's go ahead and type it into the graphing calculator. I'm not going to erase that. I'm just going to turn that equation off so that it doesn't graph. And I'm going to put my y equals 0.1542857143x plus 34.34. Okay, and that's the graph that or the line that I had graphed through the second and last points to try and best fit that data just visually. Okay, now we're going to do something we haven't done before. We're going to run a linear regression on the data. Then we'll save the equation in the graphing calculator and compare the graph that I did visually with the graph that the calculator comes up with for the linear regression. Now, depending on the operating system that you have in your calculator, some of the screens and the choices may look a little bit different. So just play around with that and figure out what your calculator needs in order to do this regression. I'll answer any questions by email. Just send me if something's not looking right and you can't figure it out. So we're going to go into the stat menu, and this means that you're working with the stats that you have entered into list 1 and list 2. We're going to scroll to the right to the calculate menu. You see that the line regression ax plus b is option 4. So you can choose option 4, and it defaults to be list 1 and list 2. Now later, if you needed to change this, you can change it by using different lists here. You can see the lists that are on your calculator. So, sorry. There we go. If you wanted to change that to list 3, you can do that, but we want to keep it as a list 1. So we'll just say second, list 1. Okay. And we want to store the regression equation. So we'll say in here, we're going to store the regression equation. What we'll do is go into this vars button. This is short for variables. And we're going to save this as a y variable. We want to save it as a function. And we'll store it in y sub 2. So scroll down and hit enter, or just press 2. So we're going to store this regression equation in y2, and then go ahead and hit calculate. So this is the regression equation your calculator has come up with as a line of best fit. And it looks pretty close to what we did with just a visual fitting. Let's go ahead and look in y equals. Now you can see there it's stored the regression equation in y2. I have my y1 turned off right now, so let's just see the graph there. And it doesn't go exactly through that second point. It kind of goes between, above and below the first and the second point. So it's slightly different from the model that we did just by eye, but boy, it sure is close. That's the equation that they had us try. That was not a good fit. Let's go ahead and put in our equation that we came up with just as a visual, a good visual fit. Oh, I have an extra 0 right there. Just delete that. X. We'll put a few more decimal places. 154, 2, 8, 5, 7, 143, x plus 34.34. Let's see. The graphs are really close. Now if you want to see a little bit more in your window, you can see we've got from 16 to 64 is what our window is right now. Let's say we go to 200 there and do a zoom fit. That's option 0. Zoom fit. And even way out there you can see it's actually pretty close. So yeah, very nice fit. Alright, so they're actually quite close. The one that we did by hand, just visually looking at those points, and the one that the calculator came up with are very close. Now, this is because the data that was given is very close to being exactly linear. So you'll have other data sets that are not quite so nice, and it'll take a little bit more work to do it manually. So we just default to letting the calculator do it. Example 4 is on U.S. population. The total U.S. population for selected years beginning in 1960 and projected to 2050 is shown in this table with the population given in millions. So we need to first align the data to represent the number of years from 1960, and then we'll draw a scatter plot of the data. So again, number of years from 1960, this is going to be 0, 5, 10, 15, 20, 25, 30, 35, 38, 40, 43, and then they've jumped to 2025, so that's going to be 65, and then they've jumped to 2050, so that's going to be 90. So be careful not to fall into a pattern of just going by fives. They will throw different numbers there at you. So we're going to make our scatter plot. So go into your calculator, stat. We're going to edit. Now, one thing you do is you can scroll up onto the list name and clear and hit enter, and it'll clear out everything in that list. Or if you like, you can just overwrite the data. So I can do that. Okay, again, double check, make sure that you have not made any kind of typos. Okay, and there's also the opportunity for error that you made your x values incorrectly, so make sure that you're checking that as well. Alright, and then list 2, we'll enter that. They've already scaled the outputs for us. Alright, you'll see you can't see all the decimal places on there, so if you want to double check, you need to actually scroll through the numbers. So we're going to just scroll through, make sure we didn't have a typo anywhere. Also, be checking, make sure that you've got the right numbers paired together. If your lists are different links, that's a good clue that you've got a typo somewhere. You've misplaced some of your numbers. Just being real here with you. On 10, it's supposed to be 205.052. So 205.052.24. Okay, so double check. Your calculator will calculate something based on what you feed it, so you make sure that you're feeding it the correct data. Alright, so we have, going to y equals, why don't we clear out those equations we had before. Our plot is already on, and we've put our data in list 1 and list 2, which is default for it. So we can go ahead and do a zoom stat. So you can see that the data is sort of in a line there. Go ahead and save your scatter plot. Okay. And now we want to create a linear equation that's the best fit for the data, where y is in millions and x is the number of years from 1960. So we can do that on the calculator here. We'll go ahead and go into the stat menu, and we're going to calculate a linear regression. List 1 and list 2, we already have our data in those lists, so that's fine. Go ahead and store the regression equation. Even if it's not telling you to, you may end up needing it later, so it's best to go ahead and do that. Store the regression equation. So we go into our variables. We go into y variables. We want to save it as a function, and we'll go ahead and save it in y1. Hit enter, it goes down to calculate, and then you're ready to go ahead and get that calculation. So y equals ax plus b is going to be y equals 2.61x plus 177.19. Alright, graph the equation of that linear model on the same graph of the scatter plot and discuss how well the model fits the data. Well, we already stored it in y equals and to many more decimal places than we recorded on paper, so that's good. There's our line, and it fits pretty good. There's a couple of outliers. It's a pretty good fit. With a couple of slight outliers. Now we want to align the data to represent the years after 1950 and create the linear equation that's the best fit for the data. So we're going to change these numbers to be 10 more than what they were. If we're going from 1950, we're just going to add 10 to each of those. So let's do 10, 15, 20, 25, 30, 35, 40, 45, 48, 50, 53, do a 75, and a 100. Now go into your stat and edit, and you can just overwrite those numbers. You don't have to clear out your list. And you can see I missed hitting enter somewhere right there, so just go back and fix it. Okay, double check and make sure all of your entries are correct. Okay, and then we'll go ahead and make our linear equation. So we're going to go stat, calculate a linear regression, same list, list 1 and list 2, but let's not store this one in y1. Let's store it in y2 so we can not lose our previous equation. So there we are. Y equals 2.48x plus 157.94. And I see another error up here. I entered 1 instead of 10. So, and I can also see that I entered a 1 up there instead of a 10. So remember, always double check. Now we can run our regression. So we're going to go to Stat, Calculate our linear regression. We're taking our data again from list 1 and list 2. Now we can store our regression equation. Go to Variables, Y variables. We're going to store it as a function, and let's store it in y2 so that we don't lose our other equation, because they're going to want us to compare. So calculate, you get y equals 2.61x plus 151.12, so 13. Alright, and then let's look at the graph there. And there is a difference there. So if we look here, y equals, you can see the red, it's moved. Okay, so the line is over here and the data moved as well. It shifted over. So how do the x values for a given year differ? They differ by 10. They differ by 10 units. So we're going to use both of the unrounded models to estimate the population. Let's see, in the Y1 model, year 2000, x would equal 40, and the year 2010, the x is going to equal 50. In the Y2 model, if we had the year 2000, then the x would equal 50, and the year 2010, the x would equal 60. So what we can do is go to our table here, and it might not even be set up to where we want it. We want to start at years 40, 50, 50, 60. So let's go into our table set and start at 40. And we can actually change how much the table is changing by. So we can change it by tens and just have all of our data real nice set up in the table there for us. So you can see in Y1 we've got a 281.46. Okay, so y equals 281.46. And in the Y1 model for 2010, when x is 50, we have 307.53. So y equals 307.53. For Y2, the year 2000, we have to use an x of 50 because of the way that we aligned the inputs. So 50, we get 281.46. And then in 2010, for that Y2 model, we have to use an x of 60, and we get 307.53. Are the estimates equal? Yes. So the models look different. The slope is the same, should be the same. The only thing is that we have shifted that second model to the left by 10 units. So you used different inputs for the year. When we apply these models, if you are trying to predict something that's between the data points that's given in the table, that's called interpolation. But if you use your model, that regression line equation that you've made to predict outside of the data points, then that's called extrapolation. There's a thing called goodness of fit. The goodness of fit of a line to a set of data points can be observed from the graph of the line and the data points on the same set of axes, and it can be measured if your graphing utility computes the correlation coefficient. The correlation coefficient is a number r between -1 and 1 inclusive that measures the strength of the linear relationship that exists between two variables. Now, the closer that the absolute value of r is to 1, the more closely the data points fit on the linear regression line. Now we're going to use the model that we created an example for. We're going to compute the population of the US in 2010. Is this an interpolation or an extrapolation? If we use Y2, where the data was based from the year 1950, then the year 2010 is going to be 60 as your input, and we get 307.53. So the population in 2010 is 307.53 million people. Is this an interpolation or an extrapolation? This is going to be an interpolation because the year 2000 is in between the data points that were given. Now we're going to compute the population of the US in the year 2080. Let's say that we use the same model. If we had the year 2080 and we're using our second model that is aligned to the year 1950, then we need to go to an x input of 130. So x equals 130, and we can see there 490. So the population in 2080 projected is 490 million people. And is that an interpolation or an extrapolation? It is an extrapolation because the year 2080 is outside of the data that was given. Even if they had given us, tasked us with finding the population in the year 1980, that is outside of the given data points. It's not between the beginning and end points of the data, so it would be extrapolation. Now we're going to compute the correlation coefficient and see if the model is a good fit. Go into the mode of your calculator, and if you scroll down to Stat Diagnostics, the default is that is turned off. So scroll over to on and hit enter. Now you have turned your Stat Diagnostics on. Okay, it'll give you those stat diagnostics when you do a regression now. If you reset your calculator, then it'll reset that to be off, so you'll have to go back in there and change it once again. So at last entry on our data, we had based our our work on the y2. So let's go ahead and run that again. Go stat, calculate. We're going to do linear regression, list 1 and list 2. Store the regression equation. We don't have to because it's already in y2. But you can go ahead and calculate. And now you see these extra things that show up. Our correlation coefficient is the R. We'll be talking about R squared later in the course, but right now we have an R value of 0.997 about. And so is that a good fit? This number, the absolute value of that number, is very close to 1. So we can say yes, the model is a good fit. That wraps up today, so go ahead and try your homework and let me know when you need help.